Hello and welcome back. I hope you enjoyed that break and a bit of stretch and running or jogging on the spot. Anything to get your going. Okay, next we're going to see about the two design flows. The first is the software design flow. As you know, you have to write coding. So you write the coding in IDE, which is the integrated development environment, and this is fed to the compiler, where the compiler gets the code and then it generates the object-oriented files. The object-oriented files are then linked to a linker through the linker, and the linker is the one which gets the final code and changed to hex format, and the hex format is the one downloaded to your target microcontroller. So first the code is written in the IDE, then it is programmed via an emulation hardware that from the linker, whatever you get the hex code, you can program that to the target microcontroller through a programmer or a JTAG, and then you can test its functionality. So if there is any bug, then you again go back to the coder team, the development team, and ask to cover up all the um, functionality. So once your code is bug free, then it's released for production to do their things to integration. So this is about the software design flow. The next one, okay, so as a whole, that will be done within about 3 different teams in a software team. So one will be doing software testing, one will be doing software and development. There will be a few people who just concentrate on programming the device. So this is a software design flow. The next one is the hardware design flow. As you would know, you are at this stage, you know what basically what components and what modules you need. So whatever the senior engineers written scribbled in the paper, you have to bring that to a software. So we use sorry, excuse me. We use the available things out there in the market. The bigger one is Cadence, Arcade, or Allegro. Altium Designer in Australia, which is really famous. KiCad, there is Eagle, there is Mentor Graphics Pad. So any of those will do the job. So first, the flow goes with the schematic design. Whatever you want to see in the PCB design, it's all connected through components with wire connections to complete the schematic. So then you convert the schematic to a layout. So layout is like a pre-PCB where you route it, and the 2 different colors shows different layers, like a top layer to a bottom layer, just to give a differentiation for manufacturing and also for your debugging. That really is helpful. So once you meet through the logic design requirement specifications all met, then you generate files for assembly people to make that board for you for prototype testing. It's called Gerber file, so you give that to the manufacturing company and they will make the board for you. And the third step is to do the assembling and testing of after production. So it is a cycle. So if something doesn't work according to functionality, you sit with your manufacturing company and discuss about how you're going to fix it and all that. So that's the general hardware design flow. And in the design process, there is 3 major processes are involved. So the first is the simulation. The simulation is a software check. There is no hardware requirement. You just run that code into a simulation tool, and it gives you the input and output, and you can see visually. So this helps to reduce the design time before moving into actually creating the real design. So that's one process, that's simulation. Then once you verify that the simulation, whatever code you written and according to functionality it works, then you move to evaluation. Evaluation is when any microcontroller or processor companies, when they release one to the market, they also release their evaluation board with reference schematics. So you can buy that and then you can write a code for that and you can test that first. If all goes well, then you can test on your code into that and make sure that is working okay. Then if both works okay, then that's when you actually go to a process called emulation. Emulation is a process where you connect both the hardware and the software through a programmer. In this case, we use a JTAG. JTAG stands for Joint Test Access Group, where you actually connect the target board and you start to debug for any problems or check for functionality. So those are all the three process used out in the market, and you will be more familiar as we move along with all the different process. And when you get into the industry, then you will have the real feel about it. But this will really help to land in that beautiful job. Okay, then we talked about safety in the first session. So every circuit or every PCB has to sit in a enclosure as a chassis or a cabinet design. So if it's only a prototype model, then you can use just a 3D printer and you can just mold it with that, or a molder will do it. But if it is much more bigger complex design like FPGA, where there is more BGA is involved, then another thing called laser cutting on its using CNC details, so fine precise cutting. So that's, again, you need to think about the cost into consideration. That's a bit expensive to do with CNC machines. And the last thing is test jigs. Test jigs really come in handy when you want to test a large quantity of the manufactured boards. So the designers should also come up with their own test jig, so that they can check for each and every functionality in that circuit board. The test jig comes with power pins. So what the power pins like this will link to the boards on the top, and that hits to run the test. Basically, the test code is fired into this, and it checks all the functionality, whether it's covered or not. So the main purpose of the test jig is when a person who has got no knowledge about design, he can also run the functionality check to help you to make the process faster. So that's where the test jig comes in handy. So anyone can help to get that out of the way to the customers. To recap about the embedded system design, first you got the idea, so you gather that and you chose the idea, and then you decide about the application where it's going to be used and what are the features and the overall cost about the product and the processor cost. And once these two are determined, then you select the right process, going through those process board which is good for you, and its packages. Again, I talk more about package. So like for BGA, you need additional oven, so that adds to the cost. So while you do that, the software team can also perform the coding level, either C or assembly language or graphical, according to your project needs. And then you design and fabricate the PCB, and once the PCB is designed, then you do the components assembly, and then you do both the integration and then the testing. So this is the recap of the embedded design. Okay, so in a nutshell, we have covered the differences between all these process and controllers, MP, microprocessor, microcontroller, DSPs, the CPLDs, the FPGAs, SOCs, and TPUs. And we covered about a selection of packages, so what package is really fit for your purpose, for your project needs, and the processor selection criteria. Remember to look for that benchmark, so you need to look for that benchmark to clear to select your processor. And also we saw the two different flows, the software design flow, the hardware design flow, to bring your embedded design into prototype. So you need to use those two flows. And part of doing the design process, you go through three different processes, that is simulation, evaluation, and emulation. And this is all we covered today's class. So let's get into the mindset activity today. Before going there are announcements that I would like to make. That there is more courses coming your way. It's a combo internship course where you get embedded C programming with Cortex M4, the current series program. Plus also stay tuned for long, and there is a bundle combo that's coming with all of those courses that's involved. So I'm pretty much sure you will get a lot of benefits out there, and sure this will help you to land into a super duper job out there. So please stay tuned for that. And let's get into the mindset activity. I would like to share you what my mentor, Mr. Jivarajan, has shared with me, and it changed me a lot since the day I started to listen to this particular YouTube click. It's about Strangest Secret in the World by Earl Nightingale. He's an American, and he talks about all the secrets that's behind um, out there, which you can overcome and become successful. So a lot of people watch this in America, and they were multimillionaires. So I strongly recommend you to watch it, so you will have a better mind change and better tuning, and this will also benefit you and shape you as a real good engineer out there. So please watch that, and that will be today's mindset activity. And again, you have to do this mindset involvement, please, just to get more involved with the basic from the same session. So get the 10 goals listed, and you work on the 10 goals to achieve that, and then the steps, you do 3,000 to 7,000 steps a day, and please spend at least 15 minutes to meditate or pray, and then spend at least 10 minutes to visualize about the goals. How are you going to make that happen? How are you going to make that possible? So, and then another 10 minutes to prepare about your daily plan, what you're going to do for your day, and 2 hours on the learning, taking your notes, and that covers all the points. So please post all your involvement points into the Facebook group so the others can see what you are doing, and that will motivate a lot of others also to get into the same frequency, so everyone will help each other out. So that's it for today, and thank you again so much for your patience, and please go and enjoy that lovely deserved break from the screen, and I will see you on the next session. Until then, I wish you a lovely day and a fruitful outcome with whatever you do today, and I'm signing off on behalf of A2G. It is Arul Anbukarasu. Until I see you next time, it's Huru from now, and I'll see you in the next session. Catch you later. See you.